of fluid. Normally, we think that liquid is incompressible. Even they compress, but magnitude of the compression or compression reduced in volume is very little. But in terms of other fluid, that means gases, is compressible. If you apply more pressure, it will more compress. So what is compressibility of the fluid? It's saying compressibility of the fluid is measured by a constant. It's called bulk modulus of elasticity, which is a measure of resistance of a fluid to uniform compression. That means if bulk modulus is high, that means it has high resistance to compress. So how will figure out what is the mathematical definition? It is defined as a ratio of infinitesimal pressure. That means you increase some pressure to the fluid, what will happen? The volume will be decreased a little bit, right? So this bulk modulus of elasticity K is defined by the ratio infinitesimal increase of pressure to the resulting relative decrease in volume. You remember, not decrease in volume, it's saying relative decrease in volume. So decrease in volume, how much? Normally expressed by dV or delta V, right? So if original volume is V, then relative decrease in volume will be dV divided by V. Okay. So if we apply over here, it's saying infinitesimal pressure, very small pressure. Say you increase pressure by delta P. Then what will be relative decrease in volume? That volume will be delta V divided by V. And this dP, I will figure out. Final pressure, that means P2 minus P1, right? And pressure is increased, so this value will be always positive, right? If you apply pressure, volume will decrease. So how will figure out the dV? So dV equal to V2 minus V1. Which one will be bigger over here? Obviously, V1 was bigger and V2 will be reduced because if you apply volume decrease. So this value you give a negative number, right? So bulk modulus of elasticity is always a positive number. So in the definition, that's why they put a negative sign in front of this term. Okay. So it is defined by K equal to minus dP divided by dV by V. What is the dP? Change in pressure, and dV resulting change in volume. And V is the original volume of the fluid. And this definition we can express in terms of density of the fluid. So let's see how we can do it. Did you see a file over here with mathematical equation?
Yes, sir. Yes, sir.
Okay. So you see, this is the definition of bulk modulus of elasticity. And volume, if you have unit volume, then you multiply by density, what will be the result? Result 1. So unit volume into rho equal to 1. Then you just differentiate this term, you get this one. V dot dV d rho plus rho into dV equal to 0. So you just rearrange the equation. In this part, you take right hand side. From here, you make a ratio. So you see dV by V equal to minus d rho by rho. Then this value is substituted right over here. Then this minus sign right over here, it will be positive. So finally, you are getting K equal to dP divided by d rho by rho. So definition of K, you can express in terms of density, also in terms of change in volume and change in pressure. So K equal to minus dP divided by dV by V, or you can write down dP equal to d rho by rho. So when you use the pressure or volume, depending on the situation, if density is given, you use this equation. If volume is given, you can use this equation, but it gives you the same result. And the bulk modulus of elasticity K, it is function of pressure and temperature. You see there is a dP, that is K function of pressure, and over here d rho by rho, that means it's ratio. Okay, and pressure also depends on temperature. That's why they're saying K is function of pressure and temperature. And unit of K, what is the unit? You see, even talk about this one, both this one have the same unit. So only have change in pressure. That means unit of K will be same as unit of pressure. Okay. Then bulk modulus of elasticity, normally expressed by K. If you inverse it 1 by K, that is called coefficient of compressibility, and sometimes it is expressed by term beta, Greek letter beta. Okay.
Sir, one question. Why in the original equation it is minus dP by dV by V?
Yeah. How come is positive? That you're saying?
No, sir. Why in the original equation it is minus?
That's what we already expressed. Explaining that change of pressure will be positive, right? And what about change of volume will be negative. So this term, that means change of pressure and change of volume. Change of pressure is positive, change of volume is negative. So bulk modulus of elasticity is a constant, and it has to be a positive number, not the negative number. That's why to make it negative, we need to put a minus sign here. Got the answer?
Yes, sir.
Okay, that's the reason. Okay. But it's good. You ask question. You have confusion, immediately you can ask question. Okay. Other property of the fluid is called surface tension. So surface tension, what does it mean? Tension means something you pull out, right? Something able to take some load, like piece of paper. The top surface, I can pull it, or I can put some stuff, even 0.5 gram or 2.5 gram, I can put it there. It will take that load, right? So in the liquid surface, also we have ability to take some force or some load. Okay, work like a membrane. Membrane means very thin material, Bangla, patla material, like this one. Okay, so let's see how we can define the surface tension. So liquid have both cohesion, two property. Other two property. Number one is cohesion, other one is adhesion. How we can explain cohesion? Cohesion means always they try to stay together. That is called cohesion. That means you have a 5 friends, you always have dinner together, or in the campus you have lunch together, stay together, sit down together. That means both of your friends is very cohesive. They always stay together. But you think about the other 5 group of friends, they are very good, stay together, but some of their friends, if they they're visiting the cafeteria, Then they got a third group, and two friends, they join from the second group to the third group. That means they have a property of adhesion. Adhesion means to stay with something else, and cohesion means always stay together. So a liquid, if all the liquid molecule has a tendency to stay together, that property we call it cohesion. And if they don't stay together, but they like to adhere means stick to something else, that property is called adhesion property. So due to this cohesion and adhesion property, it's a both of which are found molecular attraction due to the cohesion and adhesion property. So let's explain what is the cohesion and what is the adhesion again. Cohesion enable a liquid to resist tensile stress because they always like to stay together. The bonding is strong. So even if you put something, they'll like to carry that load. Now you might have the liquid surface, how it can carry load. If you put your pen in the liquid, immediately it will fall down, it will sink, right? But sometimes you might observe that some insect like mosquito or other insect is just staying top surface of the water in some lake, dirty lake, you might see. But insect is not weight free, it has certain weight, right? Might be 1 milligram or less than that, or might be higher than that. So what does it mean? You see 10 insects, they stay together just walking over the water, but you don't see any deformation in the water. That means liquid has some ability to carry some load on the top surface. Okay, so that will be figured out. So it's saying cohesion enable a liquid to resist tensile strength. Why the tensile strength? Because this is a paper. You put some load, then it will bend. But this surface, it will feel a tension. So it's saying cohesion enable a liquid to resist tensile stress, while adhesion enable it to adhere to another body. Give you another example. You put your hand in the water, your hand will not be that much messy. What does it mean? That means the water molecule has more adhesion property. They don't like to stay with my hand. But you put your hand in the honey or tar, your hand will be more messy. That means they have some adhesion property. They like to adhere with my hand. Okay. But if you see mercury, a drop of mercury, you put in your hand, you do like that, you see in the hand the mercury will move. And they stay intact. And if the mercury bubble or drop, it will not break down, even if you shake your hand. What does it mean? That means all the mercury molecules, they have very cohesive property. They don't like to stick with my hand. If you put in a tube, you will see, if you move the tube, shake it, you see they immediately move. But they don't like to stick with the wall of the tube. That means they have very cohesion property. So it's saying the adhesion enable to adhere to another body. Due to intermolecular cohesive force, a membrane or skin that seems to form on the free surface of the liquid, that is known as surface tension. And it has some force carrying capability that is called surface tension, expressed by Greek letter sigma. For example, a small needle is placed gently upon the water surface. It will not sink, but it will be supported by tension at the water surface. And it is expressed tensile force per unit distance. That means surface tension sigma equal to F by L. What will be unit? F is the Newton, L is the meter. So unit will be Newton per meter. And you see this picture. You see, what you see? That the insect top surface of a liquid, it seems like little will deformed due to the weight, but this insect is not sinking. That means this top surface of the liquid just work like a very thin material like paper, or more than more thinner than the paper. Just to give you an example. And sometimes you might see in your eye that some insect just walking over the water. Other property of what is the capillarity of the liquid. So it says liquid have both cohesion and adhesion property. When cohesion is less effect than the adhesion, then what will happen? That means adhesion is dominant. If liquid have a more adhesion property, then it will weight a solid surface. Whatever it touches, it will try to stick that wall and rise at the point of contact. So you see, you look in the figure A. So you put the liquid in a glass tube, small glass tube, then you see this portion of the liquid is like to stick with the water, comes out of the wall, but this portion is going down. That means you are able to see a curved surface in the tube. Why this is happened? Because this liquid A, it has a very adhesion property. Their cohesive property is less than the adhesion property. But if you look in the right side figure, you see the liquid at the wall. They don't like to stick with the wall. If they like to stick with the wall, then your all the surface will be like along this horizontal line. But instead of horizontal line, they're making a upside down curve, right? Because this fluid has more cohesive property than adhesion. So it's saying if cohesion is predominant, the liquid surface will depress at the point of contact. Depress means going down at the point of contact. Similarly, right over here, if you, what about this liquid? It has a more adhesive property. So you have a tube. Inside the tube, you have a fluid. Then if that tube you put another reservoir, other tank, then you see it has a more adhesion property. They like to stick with the wall. So you see the height over here is increased. Similarly, increase, height over here increase, height over here increase. Similarly, right over here, you see height is decreased because they have more cohesive property. They like to, the molecule of the liquid, they like to stick together. They don't like to stick or stay with wall of the tube because they have more cohesive property, cohesiveness, you can say. Okay. So this is the simple example. I think we can see on more. Any question? Anyone?
Yes, sir.
No?
Sir,
Yeah, go ahead.
adhesion and cohesion has does an adhesion and cohesion has any relation with the density?
Yeah, it should have some property relation with the density. Is more denser, but we are not talking about the density because say you have two fluids, both density same. One has more cohesive property, a molecule has more, they like to stick together, and other one, they have more adhesive property. Then what will you see? You will see the difference. Okay, but you are saying, does it depend on the density of the fluid? It might density of the fluid also. How? Because you see this small portion, this triangular portion of the fluid, it has a certain weight, right? If I simplify the view at the close to the wall, we have a fluid, this time fluid, right? So how this fluid staying over here? Along this surface, fluid will experience tension, surface tension along this direction, right? Because it has a both property, one cohesive, adhesive, but adhesive property is dominant. That means more. So this fluid also has a weight working down. So it should fall down, but it's not falling down. Why? Because it has more cohesive property, right? I'm sorry, adhesion property. So due to the adhesion, this wall fluid like to stay in the wall, so wall has a tension, attractive force, right? And already I tell you that fluid has both property, but adhesive is dominant. So some cohesive force also work along this direction. So you see, this weight of this portion depends on which value. The weight of this fluid depends on its volume, also depends on density. So your answer is that it also depends on the density, and it also depends on the temperature. You heat up, density sense, your fluid cohesiveness or adhesiveness will be sense. Okay, but right now we are learning only definition. We will think that what will be happen if a fluid has more cohesive and or it has a more adhesive property. Okay, you got your answer?
Sir, the same fluid, but I have changed the port. The angle will be changed or not? If I
Obviously,
change the port,
this angle, yeah, this angle depends on geometry, depends on density of the fluid. It obviously depends on surface tension. If fluid has a more adhesive property, there the angle will be changed. Okay,
yes, sir.
you see right over an angle theta, it will be changed. Anyway, so capillary liquid, we are continuing this one. It's saying such a phenomenon, rise and fall of liquid surface relative to the adjacent general level of liquid is known as capillarity. So what you see over here, fluid is supposed to stay this horizontal line, but if you look in the situation A, fluid is going up, not that means fluid level is rise, right? And you look in the condition B, fluid condition, fluid level is fall down, right? So due to the sense or due to the dominance of adhesive and cohesiveness, sometimes you see fluid level going up at the wall or might be going down at the wall. So this phenomenon or fact is known as capillarity. The curved surface developed due to the capillarity is called menicus. So you see this curved surface, this known as menicus, the fluid. The capillary rise or depression of the liquid can be determined by considering condition of equilibrium in a circular tube of small diameter inserted in a liquid. That means I just showing you the weight balance. By the weight balance, you can figure out the surface tension, how much surface tension is there. It's possible to figure out by how. Again, condition of equilibrium. Condition of equilibrium, where it is coming from your engineering mechanics that you learned in the last year. Okay. You see right over here. If you put water, then it is going down. What does it mean? That means it has Swiss property. Adhesion property is higher. If you put same tube, if you put mercury, you see the level of mercury close to the wall is going down. That means it has more cohesive property. Okay. So for this level, you just understand what is the cohesiveness and adhesiveness, and what is the capillarity of fluid. Okay. Other thing you need to know, vapor pressure of the fluid. What is the vapor pressure of the fluid? It's a pressure exerted by the vapor formed at the free surface of a liquid is called vapor pressure. And obviously, vapor pressure will increase with temperature. If external pressure imposed on the liquid is reduced to the equal or less than vapor pressure of the liquid, then boiling of liquid will start at ordinary or normal pressure. And for example, we are heating some or boiling some water in your kitchen. So what happens? You have free surface of the water, you are applying heat, right? Then water temperature gradually increasing, right? But how much the pressure over here? Atmospheric pressure, right? How much atmospheric pressure? 14.7. Then if you are applying heat, gradually molecular energy is increased. Molecule vibrate, water create bubble, and it leave the free surface and going to the atmospheric pressure. So you see the pressure in the liquid or in the vapor has to be higher than 14.7 psi. Otherwise it cannot leave, because atmospheric pressure trying to push him down, right? And vapor pressure try to getting out. So your vapor pressure has to be higher than 14.7 psi. Otherwise, the water will not boil. For example, if you like to boil water in top of the hill, what will happen? It will boil quickly or it will boil slowly. It will boil quickly. The top of the hill, your vapor pressure or atmospheric pressure is lower than bottom of the hill. Say right now we have pressure in the atmosphere 14.7 psi, or about 103 kilopascal. So 14.7 psi pressure, but in the top of the hill you might get, for example, even the height of the hill, 13.7 psi. That means in the top surface pressure is less, right? So your water will be boiled at low temperature and also quickly, because at the top surface he is feeling less resistance because pressure is less. Any question? Make it clear. Okay. Other term we need to know. What is cavitation? For example, you are working in a chemical plant. You design a pipeline, say in the fertilizer industry. Your pipeline going through certain equipment coming right over here. So if I draw a pipeline, and you might see pump, and from here there located might go some heat exchanger to make it work. Okay. So what happened? You know, vapor pressure of the liquid. You know that if you have and you like to boil water top of a hill, it will boil quickly and at low temperature, because top of the hill atmospheric pressure is less than the bottom of the hill. Right now we boil water in our kitchen, our pressure is 14.7 psi. So in the earth level, you boil water, all of the water will be boiled at the same temperature. But if you take at the top of the hill, it might boil at 90 or 80 degree temperature, because pressure at the top of surface of the water is less. That means it's certain say in pipe system. So in our kitchen, water boiling at what temperature? Boiling at 100 degree Celsius temperature, right? And what is the pressure? 14.7 psi. So you work in chemical industry and liquid is flowing along this direction. Okay, say there is a pump. Say for example, right over here, you are flowing water or any liquid at normal pressure, say atmospheric pressure and temperature. So right over here, how much the pressure at temperature? I'm just saying pressure is 14.7 and water flowing normal temperature, room temperature. But is coming right over here, then pressure is not 14.7. For example, pressure is right over here is 12 or 11 psi. Then what will happen? For example, you flowing hot water, 90 degrees Celsius temperature, and pressure is 14.7. That means atmospheric pressure. So it will not boil because temperature is not 100 degrees. If it's 100 degrees, then it will boil. But it's flowing down, coming down. When it's coming over here, then any reason your pressure inside the pipe is reduced. Say pressure is 11 psi or 11.5. Temperature is 90, same temperature. But due to decrease in pressure, right over here, water or fluid might be boiled. So you have a mixture of liquid and some bubble, and they're flowing along this direction with this mixture. And gradually, every time fluid coming over here, some portion of fluid is boiled or making bubble. That bubble, it travel with the liquid, say came in right this portion. And certainly over here, pressure is high. Then what will happen? Pressure is high, there will no bubble. It will not create any bubble. But when this bubble from here came in over here, then the bubble will collapse. So inside the bubble, it have liquid vapor, right? That vapor is explode. And immediately right this region, pressure will increase again. And the bubble will be collapse. Due to the collapse of bubble, pressure is increased. So this phenomena, this fact is called cavitation. And it has a negative effect. Say right over here, you have a turbine or you have some pump. Due to the collapsing of bubble, gradually it makes some pit. Pit means small hole on the surface of the pipeline or might be turbine blade or pump blade. And you might see if you travel through a launch or boat and you see they have a propeller, right? Propeller is rotating. What do you see? You see the water is rotating and also some water creating some bubble around the propeller. It is happening with the cavitation because due to the rotation, you learn the Bernoulli's equation. We'll teach you later on. Right over here, velocity of the fluid is increased, kinetic energy increase, so pressure decrease. Due to pressure decrease, it gets some bubble. And this bubble suddenly sometimes collapse and hit your propeller blade. And if you look carefully, say 10-year-old propeller blade, you will see there is small hole pit in the surface. So due to the cavitation, service life of turbine blade, pump propeller is decreased, or sometimes pipeline also damaged. You are designing for 20 years, but your service will be might be 15 years. Okay, so the cavitation is very important. When you design a system, you need to make sure that there will be no cavitation in the pump, in the pipeline, also in the turbine. But whatever equipment you have, there should not be any cavitation. So let's go through the word, what they're saying. It's saying vaporization of liquid will start in the flow system. Vaporization of liquid, that means boiling, right? Or vapor. In the flow system, if pressure at any point in the liquid flow approaches the vapor pressure of the liquid, resulting in the pocket of dissolved gas and vapor. Pocket means some place. Some place will be full of dissolved gas and vapor. That means it creates some bubble, and also you have a mixture of two-phase fluid. One is vapor and also liquid. And sometimes it is also difficult to handle both phases together. Okay. The bubble of vapor are carried out by the flowing liquid into a region of high pressure. When the bubble came in the high pressure region, where they collapse and giving rise to high impact pressure. When they collapse, it is a high pressure region. Again, when bubble came in, it collapsed, it increased the pressure again. The pressure developed by the collapsing bubble is so high that material from the adjoining boundaries, boundary means it might be a turbine blade or might be pipe, gets eroded horizontal, and cavities mean small pit or small hole are formed on them. This phenomenon is known as cavitation. And in theory 1, in fluid mechanics lab, I think we have one experiment on cavitation, and you can observe that when cavitation formed in the fluid system. Any question so far? No?
Sir, can you tell us some factors that cavitation is dependent? For example, if the fluid is denser, how much bubble will it create?
If fluid is
Denser, more dense.
well, it depends on it. A lot of factors involved there. Fluid has, you learn fluid viscosity, capillary, then it have boiling point. What is the boiling point of the liquid? How much pressure is there? What is the viscosity? There's a lot of factors there. In cavitation, you can do PhD on cavitation. That how you can protect the cavitation in the fluid system. Say you're working in a company, they make liquid nitrogen, or even they make the mustard oil, or they process the vegetable oil, right? So it depends on a lot of factors. It's a huge course, not the, you cannot explain with the only single term that I'm saying. But your level right now, you need to know what is the cavitation. And you remember when you design something, you need to make sure there is no cavitation. And for example, you are working Eastern Refinery and you see you have a pipeline system, and you see there is by a pump, it should run for 20 years, but it fall down or break down after 10 years. Then what will be your investigation? You should look that is there is a cavitation in the system. If you look in the pump impeller, or if you have a turbine, look in the turbine blade. Is there any pit hole is there? That means there is a cavitation. And what will be effect of the cavitation? Not only the service life reduce, performance of your pump, turbine blade, or you can say efficiency will be reduced. Okay. And now fluid pressure. What is the fluid pressure? That means force exerted by a liquid on its boundary, that is called fluid pressure. For example, you take shower, you fill your bucket with water, and this level you have the water. So what is the pressure over here? Fluid pressure. All the fluid pressure always work perpendicular to the surface. Right over here is working, right over here is working. Also working in the bottom. Similarly, working in, sorry, it should be perpendicular to the surface. Okay. Say you buy a bucket, plastic bucket, but you thin out the wall. What will happen? Thin out like a polythene or like a birthday balloon. You put water, it will expand, right? Because the wall, it don't have resistance to carry this pressure load. So what is the pressure? Pressure equal to force by area. So if you know the pressure, you can figure out how much force in the fluid. Say bottom of your bucket, what kind of area? Obviously round, circular, right? You know the area. If you know the what is the pressure at the bottom of your bucket, then you can calculate the total force, how much force in the bottom of the bucket. Okay. So it's a normal force exerted by liquid or fluid on unit area of its boundary or control surface is called fluid pressure. And it is equal to F by A, or small force divided by infinitesimal area, dF by dA, also represent the fluid pressure. Now, how to be unit? Pascal or Newton per meter square, or sometimes we express British unit, PSI. We have time? We can solve a small problem. Okay. What is saying over here? At a depth of 2 kilometers in the ocean, gauge pressure is 440 kg force per centimeter square. That means at the 2 kilometer depth of the ocean, this much is pressure. So if I make a line, straight line, this is the top surface of the ocean. Say at 2 kilometers right over here, 840 is the pressure. Density and bulk modulus of elasticity at the surface, water surface, are 1025 kg meter cube and 24,000 kg per centimeter square. That means at the top surface, right over here, if I say this is the 1, this is the 0.2. So right over here, density is given, rho, right over here, equal to 1025 kg meter cube. And bulk modulus of elasticity is given. That means value K is given over here. This two value is given for top surface, and the bottom surface only pressure is given. I can say this is P2. So it's saying what will be the density of the water? Right over here, how much will be density? That we need to figure out. What would be the density right over here? What will be specific volume? That means 1 by rho. And change of volume at this depth. That you need to figure out. So you see, this problem is related to bulk modulus of elasticity. So our formula, you need to use this formula. Now you need to use this one, or you like to use this one. We'll use the both one. We'll see. Okay. So you see, given P2 right over here, 840 kg force centimeter square gas pressure. And top surface, that means at 0.1, rho is given this much. And K is this much. I need to figure out rho 2 equal to how much right over here. Small volume, specific volume is how much, change of volume is how much, that we need to figure out. So what we will use? We use this formula. So instead the first one, you take the second one, because density is given. At the top surface, density is given, 1025 kg meter cube. So you say K equal to dP divided by d rho by rho. So you put value of K, change of pressure is 840. You see how become 840? Anyone? What is the pressure at 0.1? P1 equal to atmospheric pressure, right? I can say P atmospheric pressure. That means 14.7 psi. And what is the pressure as P2? 840 gauge pressure. I will explain later on. If you gauge pressure, if you add atmospheric pressure with the gauge, then you get the absolute pressure. So your P2 is equal to 840 plus P atmospheric pressure. So if you subtract this one, P2 minus P1, what will you get? Your atmospheric pressure will be out. You will get only 840. So that's why they put delta P 840, and this term they keep it same. Now how do you say it? This unit will be out. So from here, you can figure out this value, del rho by rho 1, this value, 0.035. Then so this is your 0 by 1. And this 0 equal to how much? Rho 2 minus rho 1. Then your 0 equal to 0.05 rho 1, and 0 equal to, I can write down rho 2 minus rho 1. Then you figure out the rho 2. Rho 2 equal to this one plus rho 1. So I just make simplify 1 plus 0.35 into rho s. Rho s means density at the top surface. So you multiply that 1025, then this is rho 2. Then they like to know Pacific volume. Pacific volume is inverse of density. So V2 equal to 1 by rho. Then they say, what will be change of volume? You figure out change of density. You have rho 1 already given. You figure out the d rho. D rho equal to 0.035 rho 1. Rho 1 is given. So you get this value. So this value is change of density. And what will be change of volume then? Then just inverse. dV equal to 1 by rho. Okay. And volume would be decrease. Any questions? Anyone?